live. Here we go. YouTube says I'm going live. YouTube says I'm live. It also says there's an error occurred. Can we confirm on phones and then we can get started?
Yep. Looks good.
Looks good on phone. Excellent. Okay, let's get started then. Let's see who we got. I think I've got some... Yeah, I've got it on sub only actually, so interesting. Didn't want those same people to come in and ruin it like last time. Spamming the chat with filthy things. With filthy things. Oh, so I don't know if anyone's actually in the chat yet because I can't see, but we have a little starter here for people to think about. Maybe in about 5 minutes we get started. If you're rewatching this, you can, skip this bit if you want, or take part. Have a look at these cubes down here. They're all modelled with unit cubes, and they've got a volume of 5 centimeters cubed. Just something to think about. Which pairs will have the same surface area? Which pairs will... Okay, that was the test. I guess I get started on this. I get, go through it bit by bit. For those that are rewatching, I think that's the thing. So obviously this is not too taxing. You've got 5 on the top here. If we're looking down at this shape. You've also got 5 on the bottom, 5 at the side, 5 at the other side. So we've got something like 20 plus the 2 at the end. So this has a surface area of the squared. Hello AMT. Howdy. I like typing, I can't tell you. I like it better than the speaking. Okay, let's do the one on the right. No surprise. The interesting thing about surface area from the top is, from the top, this one looks like a square. We've got 4 on top, 4 on the bottom. So we've so far got 8. And then from each side we have something like this, this, and this. So that's 3 from that side, 3 from that side, 1, 2, 3 from that side, and 1, 2, 3. So it's going to be 3 times 12, 3 times 4, which is 12. So I'm pegging that one. It's 20 centimeters squared. It's a good exercise in, like your spatial awareness, because I guess this kind of thing is hard for some people. It is. If you haven't played with Lego, right? These diagrams are the exact diagrams in a Lego kit, right? You got 1. This is your step 1. That's your step 2. And another thing, if you play video games, understanding 3D surfaces and environments, these sort of things help develop your spatial awareness. This one's a interesting one. 1, 2, 3 on the top, 3 on the bottom, so it's 6. 1, 2, 3, 4 from one side. No harm in doing it a bit at a time. 1, 2, 3, 4 from that side, and we're noticing a pattern here. No matter which side you're looking at it from, it seems to be the same. 1, 2, 3, 4, and 1, 2, 3, 4. So this one's going to be a jolly 22 centimeters squared again. So I guess these two are paired up. I'm doing good, thank you. I didn't read that one. I saw. It's been it's a full-on time of the life, but it's actually a really good one. How are you doing? How is the week going so far? Does it look like it's going to end well, or in fire? Fire or ice? Who knows? The bottom right. Okay, we've got 6 on the top, count properly. It's 5. Plus 5, because we've got the bottom. Moving around, we've got 2 from the left. We've got 2 from the right. And on the either side here, we've got 1, 2, 3. So 3 plus 3. So that's going to be 10, 14, plus 6, 20 centimeters squared. Ah, lovely. We do have 2 pairs in here. So these are the these are the pairs that we have for the surface area. So today what we're going to be looking at is a little bit of vectors, which was highly desired last time, especially where there is ratio. And then we'll look at a lot of the 3D shapes, which was also highly desired. The 3D shapes questions get fairly difficult, so they're going to be fun. And yeah, let's get into it. Might just clear this whole board.
This question reminds me of a similar question that I had, I think, in high school that was interesting. So is it possible to have 2 rectangles with... what was the question?
Yeah.
I think it was like 2 rectangles with the same perimeter and same area at different dimensions or something.
It's like a investigation, keep them busy. Not to be too rude about it.
I think you can prove that they have to be congruent. I can't exactly remember. Well, a question for the viewers if they want to try. Can you find 2 rectangles with the same area and perimeter but different dimensions?
That one. I do remember doing something like, there is an area, find 2 that have that, as many as you can that have that area, but your one's far more interesting. That requires a lot of trial and error. Could you do it with algebra, like?
Yeah, I think that you can prove it with algebraically that they have to be congruent.
Very interesting. Well, that's how basic questions can turn into interesting ones quickly. Let's go to this first question here. Shall I take the first one? Or you want to get your teeth into it?
You can if you like. It's up to you.
I'll go for it, but I'm wondering where it is. Yeah, here we go. We've got the old interface back, so just trying to figure out where we put them. We're going to start with vectors, as I said, and we'll go straight in where we've got vectors and ratios. So here we go. See, this is a 5-mark question.
That's the second part of it.
Oh, let's clear this page images. So I just did it bit by bit, so it would probably be vectors 1 then, I suppose, this one.
Yeah.
Yeah, and then there'll be a second part to it, which I will scale down because it's overly big, and move over here. Okie dokie. So is this something that you've? Yeah, that should be big enough. Okay. Let's always start with a nice bit, don't we? The express A to B terms of A and B. So we look where it is. A is here. First thing I need to ask, is this big enough? Can we see this okay? Because I am wondering.
Looks good to me. I don't know.
That's all right. Cool then, because I don't have a double check on that. So A to B is, so we're going from here to here. We go on those roads that we have mapped out. Even if the arrow is going the wrong way, you're probably, I'm not going to go straight to it, because I feel like if you're watching, you could probably have a go and try and get there before me, and then we sort of get there together by the end. So I'm going to go down these roads that I've already got mapped out. So that's negative 3, should I go straight there? I'm going to leave that until I'm happy with the answer. So negative 3a, I'm the kind of guy that underlines my vectors. I don't know about you. And then we're going to go up the 6b. I'm also the kind of guy that doesn't like to have a negative out the front. So I'm going to write this as 6b, and I'm going to curse the person that made this question. Why? Because they knew what they were doing. The 6 and the b, it's far too similar. So be careful when you're writing that one. Okay, you probably got there quicker than me, but good for you. What about this next one? So this is where people were requesting things like the ratio. And here it is. We have the fact that a to, I mean, you could do it however you want, but I like to label it on that a to x here is 1 and the x to b is 2. Like, you've got to compromise in a way because this might look very messy. For me, I just feel like I do it. So that's reminded me of what sort of ratio is going on there. And it says b to y is 5, so that's a new thing for us. B to y, is it? Oh no, it's not. It's already on there. That's fine. That's fine. So we've got a new thing. Goodness knows how we're going to use it yet, but let's not get too discouraged. Prove that O to x, where is that? Here, there's O to x, which is the midpoint, is equal to 2/5 of O to y. Right, that's why we need b to y. Because we now need a journey. We need to define O to y. And I can see if I go via b and then go across that new section that we've just been told about, it's a hint to say we might want to do it that way. Okay, so 2/5. First of all, we probably want to get O to x. And then, equate it. O to x, any favourite way for you, Joe? Any favourite way? Would you go up or would you go left?
Yeah, I just went, oh, well, 3a looks smaller than 6b, so I would just use the smaller number probably.
That's a good point. I'm probably going that way because, like, thinking ahead, we just defined a to b, right? So if I add that in on this diagram without graphical glitches, it looks something like this. It's going in the upward direction. Therefore, we can keep what we have here as it is, like a positive. It could be a pro tip there. So we're first of all O to x. Let's use a big space here. We're going to bring up a plan. We're going to say O to a. And we're then going to go A to O on the brain, I say. O on the brain. A to x at this point. And that's going to be made up of O to A, which is nice this time. It's going to be positive. And plus A to x. Now, this is the one that we have part of in part A. And we just got to think about what sort of fraction this means. I mean, it's a good skill to have if you've got 1 to 2 to figure out what these are as fractions. So there's 3 parts in total of this whole thing. Let's write that there. And then obviously this is 1 of the 3 and that's 2 of the 3. So how far do we want to go up that line? We want to go 1/3 of the total A to B. So we can write that in 1/3 of A to B as just a plan at this stage and take an extra line. If we do one thing at a time, we won't get too flummoxed. So if we have 1/3 of whatever we found A to B was, which is the first question, 6b, subtract 3a. That looks great. So this is OX, and it's the first part, but it's not tidy. Traditionally, you just want 1a and 1b, so we're going to have to expand those brackets and simplify. So 1/3 of 6 is 2. I wonder if I've forgotten how to maths on the journey home. Look at this anomaly. Everybody, that's not a D, it's not an alpha, it's an A. And finally, OX, I don't write it every time. Should I? It's up to you. OX is 2A, because we take away that A at the end there, plus 2B. How lovely. How often have you done a question and it's 2A plus 2B? Often. Okay, next we're going to, because we've got to prove it, we've got to see if it is equal. So we've got to find OY now. We found the left-hand side, which is OX, that's in the bag. We've got to see if we multiply OY by 2/5, will we get OX? We need OY first. OY. Kind of sounds cool to say. OY is going to go through via B, in my opinion. And that's a shame. 6B. Never use 6B. If you ever become a question maker, you have to answer it to me. I guess I'm skipping a step here as in the plan because I feel like it's fairly straightforward to do OY. Interesting that we have OY. It gives us the resultant, which is this red bit here that I've just added. Okay, so the resultant is straight there. Let's tidy this up because we only want one of each letter. These brackets are superfluous really. Let's just add them as they are. So negative B, we've got 5B. Something is shaping up nicely to look like 2/5, right? We've got 2 and 5. Something else I'd like to do is write the A first. You could argue that the first attempt at writing was neater. You would be correct. Try that once more. There we go. Right, so OY is defined, and all we have to do is prove.
Did you mean write 5B?
Totally. Like more than I could ever imagine I wanted to. I did want to write 5B. Thank you. So OY, I wonder if it's true. So we've got OY. If we multiply that by 2/5, do we get OX? Let's see. 2/5 of OY plus 5B. And if we can see here, each of these would be multiplied. Well, you can see the 5s will cancel it. So that would be gone completely. So 2/5 of OY, the 5s will go, and then the 2 will take its place. We'll end up with 2A plus 2B, which is OX. Lovely. So it is true that that this is true. We proved it. It's pretty cool. You have to define them. See, when it says prove, don't get too shaky. All you have to do is find this, and then multiply it by 2/5 and then see if they're equal. Cool. Nice. Do you want to take one next, Joe?
Sure.
Let's get you a new page, a fresh page.
I'll pick. How do I do this again?
It's alright, like resources and images.
Yeah.
I think I've opened it. Do we both see it if I open it? I don't know.
So this one, yeah, I want to do this one. Okay. Alright. So this isn't exactly ratios, but it's still vectors, so hopefully it's still useful to people. This one's more to do with equating coefficients, which is still a very useful skill in vector geometry questions. But there's 5 parts to this, so let's start at the beginning.
Always a good place.
It says ABCD is a parallelogram in which AB equals X and BC equals Y. So that's shown on the diagram. AE equals AE 2ED equals 1 to 2. So that's down here. So AD would also be Y. And as I go, usually in these vector geometry questions, if they give you a diagram, I like to label the diagram as I read the information so I don't kind of forget it. And this bit is a little bit wrong, like it's not correct to label AE as 1 and ED as 2, but sometimes I do that just to take notes as I go, just to remind me what this ratio is referring to. So you got to be careful, don't misinterpret me here. I'm not saying A is equal to 1 and ED is equal to 2, but that just reminds me those two lengths are in that ratio, so hopefully that's not too confusing for people. Alright, so then part A says express in terms of x and y, AC and BE. Okay, so AC, well, firstly let's find what that is. That's the diagonal of the parallelogram, and that's not too difficult, right? From A to C, it's AB plus BC, that's just x plus y. So for part A, we've got our AC. This is x plus y. Then we need BE. BE is down here. So that's so BA to AE is one path we could take. So BA is negative x, and then AE is we have to think a little bit. Because I made this note, I know it's a third AD. Okay, so what was AD again? AD was y. So A is a third y. Okay, so BE is going to be a third of y. That's AE. Let's just make a little note as well. Let's just say AE is a third y. And so then BE is going to be a third y take x. Okay. Alright, so that's part A. Part B. AC and B intersect at F such that BF equals VBE. Okay, so that's saying this intersection point F is such that we split this line BE into some ratio, and they've given us this V. What does that mean? It's just some unknown that represents that section of BE that is BF. So let's just make a note of that, what they've told us. BF equals VBE. Some ratio of BE. Part I says express BF in terms of X, Y, and V. So BF, well, we know BE is a third Y take X. So if we want to express BF in terms of X, Y, and V, yeah, that's going to be V, the multiple V of BE. So BF, we can say, is V, a third Y take X. Okay, so yeah, we've taken this statement and written BE in terms of Y and X. Okay. Part II says show that AF equals 1 take Vx plus a third Vy. Okay, so we know so from A to F, we're going to go from A to B, then B to F. Well, now we have BF. We know AB is X, so we can say AF is going to be AB plus BF. AB is X, BF we've just written, so let's add this on, this expression we just found, V times a third Y take X. And then let's simplify this a little bit. So combining like terms, this will be X plus X take Vx, X take Vx, plus V on 3Y. Okay, so that's V times a third Y, which I've written as V on 3Y. Then X take Vx, you can write as 1 take Vx. And they've actually left it as a third Vy, so I'll just write it as that. A third vy. Okay, so there we go. We've shown part II there. And then for the final part, it says use this expression for AF to find the value of V. Here's where the equating coefficients comes in, and the understanding of what it means for vectors to be parallel. So we have an expression for AC. Recall that AC was x plus y. And AF lies on that vector, in other words, is parallel to that vector. So any vector parallel to AC must have coefficients that are equal, because the coefficients in AC are equal. So any multiple of AC, so any scalar multiple of AC must have equal coefficients. That's a key point about parallel vectors. The multiples of the coefficients of the parts of that vector must be the same. So here we know AF is 1 take V plus a third VY. These two parts of this vector must be equal. So then we can say, to find V, we say therefore, oops, still in red. Then we say therefore 1 take V must equal a third V. And then we can use this to solve for V. So add V to the other side. A third plus 1 is 4 and 3. 4 and 3, V equals 1, therefore V equals 3 on 4. Okay, so yeah, I think that's a really important skill to master in these vector geometry questions, is recognizing well, there's the basic fundamental things you need to understand, like parallel vectors are multiples of each other, and then you need to know how to apply that in certain situations. All right, so I thought that question was useful.
Yeah.
We jump to another one. Page 1.
Should we do one more vectors?
One more vectors, okay.
What's a good vectors?
We'll do a similar one then.
Yeah, do you know which one it was?
This one, I think. Yeah, this is a similar question to the last one. So if you weren't sure about the last question, maybe you could use this to practice. If you're watching this video back later on, you can check the previous video, previous question, see how that was done, and then use this as kind of your own revision question if you want. All right. Okay, so this one says WXYZ is a trapezium with XY parallel to WZ. XZ equals 5A take 2B. That's the only one not on the diagram. The other two are on the diagram. So X, so let's write that in. That's 5A take 2B. And then ZY is 3A plus 4B. That's indicated. And WZ is 6A plus KB. That's also on the diagram, where K is an unknown constant. Here it says work out the value of K, show working to justify your answer. So notice, I guess that the slight step up in difficulty here is there's no scaffolding, so they don't give you any steps to take. It just kind of throws you in the deep end, I guess. And if you're not sure how to begin here, this can be really challenging. But I would suggest going back to those basics and thinking, okay, Well, if I want to know this unknown, what can I compare it to? Well, they've told us this is a trapezium and xy is parallel to wz. So xy is a parallel vector. So it could be really useful if I can find xy in terms of a and b, and then that maybe will help me define k. So again, going back to those kind of basic fundamentals, if you've mastered those, try to apply those in situations where you might be unsure. So here, my goal here is to find xy. So can I do that? Yes, I can, because I have xz and zy. So I can follow that path. So this is going to be 5a take 2b plus zy 3a plus 4b. And actually I should, I forget how, can you move things around in this program?
What do you want to move?
I just want to move this down.
The actual text, I don't know.
Yeah. Well, I'll just make it clear. I did xy equals xz plus zy. Okay, you can still see that. Okay, then let's simplify this. 5a plus 3a is 8a. Negative 2b plus 4b is plus 2b. So we have xy. And now we're going to use the same thing as we did in the previous question, comparing coefficients. Slightly different here. We're comparing 8a plus 2b to 6a plus kb. We want to, well, the way I'm going to do this is I want to somehow factor something out of this vector to see if I can turn it into, or get 6 as a coefficient of a. So what can you factor out of a? 8 to get 6. Or in other words, what can I divide 8 by to get 6? Well, 6 is 3/4 of 8. So if I factor out a 4 and 3, I should get 6. So if, in other words, reverse that, if you multiply 6 by 4 and 3, do you get 8? Yes, you do. So 6 divided by 3 is 2, times 4 is 8. And then 2 divided by 4 and 3, factoring fractions isn't so straightforward, right? But, well, could take the long way. 2 divided by 4 and 3 becomes 2 times 3 and 4, which is 6 on 4, or 3 on 2. So this should be 3 on 2b. Okay. There are slightly different ways to do this, but yeah, basically I wanted to change xy such that we had a 6a. Why did I want to do that? Because now I know if I multiply xy by 4 and 3, if I multiply wz by 4 and 3, I get xy. And those vectors being parallel, that means k must be this coefficient of b, which is 3 on 2. So yeah, a couple of questions with parallel vectors and needing to understand how to compare coefficients and equate coefficients. There.
Awesome. As by popular request, vectors. Gotta love vectors. Alright, thanks for that. Let's move on to the main event. So we're looking, let's get rid of all of these. We're looking for now to do lots of questions on volume and area as requested. And our first one is going to be maybe a warm-up more than anything, I'd say. Just trying to get my pen. There we go. Maybe a warm-up more than anything. Got to work through in order and take it as it is. Wrong one. This one. Okay. So just to, like, I guess an introduction again back to what it means, you know, what we're doing here. This one's question, we'll call it 1A, just so I'm aware of where we're up to. So this diagram shows a metal piece of conservatory roof. Find the volume of the piece in centimeters cubed. So fairly straightforward volume. I was thinking, various different volume and surface area questions. That's what I mean by 3D shapes. And obviously along the way we'll get to talk about a lot of 3D shapes. This particular 3D shape on the side here, I mean, what is it? How would you... I'm not sure there is is that a shape? It can't be. There's definitely a delta head or maybe an arrow. But if you're going to break it down, that's basically a triangle, a rectangle and another triangle. It's not much, but thankfully it gives us the area of this entire cross section. So if I shade it in, we have the area of this cross section. And when we have prism, it's like a loaf of bread in a way, right? So if I just draw these lines on here, you've got to think about them as like slices. And the slices are so thin, but we can't really see them that well. So we just imagine it's like a loaf of bread that's been sliced, like this. And we're going to say that if we've got the end surface area, that's sort of got its own volume and it's wafer thin. And it's going to be multiplied by however many, like it goes back, like the repetition. Obviously I've made these lines very spaced out, but in premise it's like that. How much do we have? We've got infinitely many of those slices going backwards. So with all prisms, I'll just call this volume of prism. It's going to be the cross section area multiplied by the, we call it the length of the shape. And in this case, we have the length here is 3, and the cross section is given as an area. You see it's centimeters squared there. So we just plug it in. And 16 multiplied by 3 will give us our volume of the prism overall, 48, and this time centimeters cubed. It's cubed because we have 3 dimensions going on, but I think I've missed a detail. Only because I'm looking at this thinking, no, it's not that easy. And if you're screaming out thinking, oh, yeah, well, type it in chat. Tell me how I went wrong. Can you see, Joe?
3 meters.
Yeah. So there's always something to watch out for. Units, hey. So let's convert first. This is the question, the gift that keeps on giving, because we've now found a juicy extra question inside the question. So if we get it to centimeters, it's easier than converting the centimeters squared, in my opinion. So we're now going to go back and multiply properly. So it still will be 48, but we're going to have another couple of zeros on there. Centimeters cubed. And how do we even have an understanding for 4,800 centimeters cubed? It doesn't really do anything for me in terms of how big that thing is or how much it weighs. But there you go. 4,800 centimeters cubed. So it's just a little introduction. You've got to know your prisms, right? You've got to know how to work with prisms when we get to the later ones. Do you want to take the next one?
Sure.
It's not gonna surprise you. You'll be okay. That was 1A. This was 1B. Here we go.
Yep.
In the bag, sir.
Surface area. See, the volumes are nice. Surface areas are what do I find painful?
Really interesting. Surface area of cuboids.
Well, just the process. All right. So the diagram shows some steps. Find the volume in centimeters cubed and the surface area in centimeters squared. Okay, well, let's start with the volume because that's, as I said, what I prefer. And when you're given kind of compound shapes like this, I would suggest splitting them up. So we can turn this set of steps into 3 rectangular prisms. And it's easier to find the volume of 3 rectangular prisms than, you know, a shape like this. And they've given us all the dimensions. So the height is 20, the width is 20. So we know the surface area of the end here is going to be 20 times 20, or 400 centimeters squared. So this area is 400 centimeters squared, and then to work out the volume of that rectangular prism, multiply it by the length. And we just learnt we need to check our dimensions, make sure they're all in the same unit. So this says 1 meter. We're going to convert that to centimeters. So that's 100 centimeters. So then the volume of this rectangular prism, which is actually a third of this shape, is 400 times 100. So I'm not sure how to notate this. I guess I could say 1 step. The volume of 1 step is 400 times 100, which is 40,000. Yeah, 40,000 centimeters cubed. And then the total volume, I know, well, each of these rectangular prisms is the same. So I'm just going to multiply that by 3. That's going to be 40,000 times 3, which is 120,000 centimeters cubed. All right. So that's the volume. Then the surface area, I've got to work out all of the different surfaces. So, well, we already worked out 1. Well, I guess this isn't so bad. The surface area of this face here is going to be 3 times 400. So this face, we call that, let's just say surface area. Let's just do kind of a progressive sum. It's going to be 400 times 3 plus, and then let's also multiply that by 2 because we have one on the other side. On this, looking from the back, we'd have another one of those. So let's multiply that by 2. Then let's add on 1, 2, 3, 4, 5, 6, 7, 8. Lots of those rectangles. So on the bottom, there'll be 2 more. And then on the back, there'll be 2 more. So there's 8 of those rectangles, which have dimensions 20 by 100. So that's 8 times 20 times 100. And then we just need to do this calculation. So that's 400 times 6, 2400, plus 2000 times 8, 16,000. So we've got that correct. 18,400 centimeters squared. Should be fine. Okay, there we go. Not so bad.
Well done. Not so bad after all. I think the biggest mistake there is not using the units correctly, right? So just making sure that you've got the squared rather than the cubed.
Also, well, still, I mean, with some, like, thinking in 3D is a real challenge for a lot of people. Like, I don't know if it's something you just know how to do or not. I'm not sure. I don't really remember how I learned how to do it. But looking at a 2-dimensional figure representing a 3D shape, can be a challenge. And it might, I don't really like to say this, but it might be something you just know how to do or you don't. I don't know. But yeah, I mean, learning that, or learning to imagine this shape in 3 dimensions is also a skill, I guess. Like learning what would the other side look like, what would the back look like, and imagining those areas.
Do you feel like drawing the net would help?
Yeah, yeah, maybe that's how I kind of learn. So to work out the surface area, drawing all of the sides and being able to see all of the sides laid out like that might help.
Yeah, yeah. I reckon I've lost my drawing tools now. There, I'm gonna get rid of that. All right, so I think that's a good couple of warm-up questions, and we'll get on to the harder ones, eh? I have to clear some of this stuff though. Images and drawings. What is that? Okay, that's cool. And I found this one rather interesting. I like the sound of it, and I'd be interested to work it through.
Yeah.
I'm not sure where I got that one from. Oh, that was 3D intro. Okay, cool. Yeah, so obviously never seen it before, but I think it looks interesting enough. A spherical stone ball of a diameter 10 centimeters. So let's just make no minds about this. Diameter is going to be all the way across, and that's fairly a large stone ball. Of diameter 10 centimeters is dropped into a cylindrical barrel of water, hopefully not glass, and sinks to the bottom, probably rather fast. The ball is completely covered by water. By how much does the water rise in the barrel? So I think this is a fantastic question, to be honest with you. It's about, how you can morph the different volumes into different shapes. And I guess it requires us to make an assumption that this is as dense as the water. I'm going to take this moment to just talk about an interview for Oxford. So there was this really famous interview question. You go and you get told this fancy story because it's one of the most interesting questions I've heard. And they say, how do you measure your head? I don't know how you would ever get taught this in normal school, but how do you measure the weight of your head? And the answer, well, you can come up with a number of things. It's up to you, really. Let's talk about what you might think about. You might think of, putting it on a scale. Unfortunately, it's attached to your body, and so that weighs it down, right? Have you heard of this question, Joe?
Yeah, I think so.
Yeah, they may have gone through it. And you think, okay, well, let's cut our head off. Clearly, it's not possible to do something like that. So how do we do it? But it relies on this idea that your brain is fairly similar in density to water. And so if you put your head into a body of water and you measure the displacement and turn it into some sort of metric, we can get the weight. It's fairly similar in weight to the water. But it's an interesting question, and I think this would spark the roots of being able to answer that when you get to Oxford. So, bearing in mind this is 10 centimeters cubed, we want to probably find the volume of this sphere, and the volume is going to be 4/3 pi r cubed. Well, mostly the times you'll get this, but if you don't, there it is. And we want to make sure we're using radius instead of the diameter, which we have here. So radius being 5 centimeters, and that's going to go in to the calculator, my end anyway. 4/3 times the old pi button. Doesn't say leave it in terms of pi. Good. Okay, we'll carry on then. Times, what have we got? 125. We'll do that without a calculator there. So, how very noble of me, you say. Volume of the stone, is it? We're calling it a stone. 523.59877756. I wonder if some people are thinking, why is he writing all of the decimal places? And well, really, I write the decimal places. It's a habit from a university course where you go to 10 decimal places and analyze, the effect of calculations and accuracy. And I feel like, even if you're not doing a course like that and you've developed a weird habit, that it's good to have it, because if you go wrong and you have to go backwards, you don't have to write it on your calculator again. You've got the full digits that you would see on your calculator. So sometimes it can be useful, but I just like to leave it there. You don't want to round it too early, because otherwise you end up with inaccuracies later. So I've got the volume of this thing here, and this is going to be in centimeters cubed. And the idea, I think, if I'm not wrong, is that we equate them, and I'm just going to rub this out because I accidentally did this. We equate this to some sort of increase around the side. So all of the water will have risen by the same amount of volume. And I believe that we can talk about this in the same sort of way. We've got the volume of the water and the stone being the same density, therefore it will just rise in the same way. So I think firstly I'd like to work out the difference here. So an expression for the water, would that do it? I haven't done this. So the diameter of this particular, if I get a pen out, that would help. Diagram of this particular, what they're calling it, a barrel, has a diameter of 40 centimeters. So we're going to talk half of that, 20 centimeters as the radius. And we've got some sort of height in here that we don't know what it is. Well, that's interesting. I would probably like to have seen that, but I don't suppose it matters. I suppose we'll get an expression for it. If we say that was we'll call it height, then we would get an expression here, which would be pi r squared, which we already know r, multiplied by h. And that would be the volume of the barrel. Am I going in the right direction here is the question. We don't know. All we're doing is seeing what we can do. I can't actually, because I haven't done this one before, so I can't see 100% where it's going. But I imagine there's some sort of difference here. And that this difference is the thing that is going to be equal to our volume increase. And it will be something like this. So we kind of want to talk about a shape here, a cylinder with a volume of 523.59 etc. centimeters cubed. And the expression of this is going to be dependent on a number of things here. The height itself is the unknown, but so long as we have an equation, we can rearrange and find that height. So it's going to be okay. Let's actually plug some numbers in and see what that would look like to our absolute limit. So pi is going to stay the same. We've got the radius here, so r squared is 400. And h is the thing that we ultimately want to find, which is the way that that's increased. In a way, it's like they could have asked this question as this. They could have drawn a cylinder and a sphere and said that these have equal volumes, and then you have to find the dimension of the height of the cylinder part. But I quite like the way they asked the question. sort of a context-based thing. And we know that then pi, what should we do this? I'm going to run out of space either way. Maybe we should start putting the numbers at the front. Is equal to 523.59, etc. centimeters cubed. And that's what I know. If it has a volume of that, what's the height? That's the unknown. So we're just going to do the number, which is still on my calculator, and therefore divided by 400 pi. And it turns out to be fairly nice if we leave it as a fraction. So I'm going to leave it as a fraction. And h, let's do my working out. H is equal to 523.59 centimeters cubed divided by, in fact, there's probably a little bit in the way there. We know it's all in centimeters cubed. We'll do it at the end. Divided by 400 pi. And this is a rational number on the bottom. So the fact that it turns out to be 5/12 is a miracle. But yeah, 5/12. And since this is a singular dimension, we're going to be measuring that in centimeters. And for though, does it say, no, it doesn't say to give it in a decimal place, but if we did, decimals give us a better idea of exactly how tall it is. I'm going to round it to 2 decimal places. I think that's done. How much does the water rise in the barrel? Would you agree with that solution?
Good. About 0.5 centimeter. Interesting, isn't it? Such a big stone, but then the barrel is quite wide as well, 40 centimeters diameter. So.
Yeah.
So you can just do fractions all the way to end up with this. So if you leave this volume as,
that's true,
3 pi times 5 cubed, then you end up with the equation 125
500 over 3. Yeah.
3 pi equals 400 pi h, and then everything cancels. This is
500.
Yeah, 500 equals 1200 h. So that's how you get. But yeah.
Oh, that's interesting. Yeah. I think I was feeling my way through the question. Sometimes, if you don't, you can't jump straight to it. Fractions are very nice. But I was thinking, well, how does this work out then? It's kind of nice. I'm going to write down everything I know as I go along. And it sort of came to me that, that was an equivalence. Very nice. All right, you're up. Let's see what we got for you. Let's clear. Okay, the board clearing is not working. Oh, that's rubber. That will make a big difference. All right, let's get rid of that. Bye-bye to your writing and drawing. I'm sorry. Okay. I really liked this one. That was pretty cool. That was cool. Do you want to do a hard one or an interesting one?
I was thinking of the cone and the sphere. It's a very typical kind of question, but I don't mind. Whatever.
This one here.
Sure.
That looks a pretty cool one, actually. That funny symbol up there is pi. I think it's just a really dodgy font. So you will get that from time to time. But that is pi.
It looks like... it just looks like an N, but okay, yep. I trust you, it's a pi.
It has to be. Well, this one's so cool.
If you write tau, it's like that or something. What's half, that symbol for half of pi or 2 pi?
Yeah, no, I don't know. This is just a very funny font, I think. You see all sorts of strange fonts. And pi is technically a serif font, right? So where things stick out, that's like a serif, right? So what we're probably looking at is a sans serif font where they wouldn't have anything sticking out.
That's cool.
Anyway, there you go. A bit of calligraphy in the math
That was
lesson.
yeah. Okay. Find the volume of this compound shape in terms of pi. All right. Well, we have almost all the dimensions we need, except the radius of the hemisphere, which we can find. And actually, this is a nice Pythagorean triple, right? 12, 13. Wasn't it 7? Yeah, 7, right? No, not 7. 5. Yeah, 5. 5, 12, 13 is a Pythagorean triple. But let's check. So we know 13 squared equals 12 squared plus something squared. Let's just call it x. And so x squared is 13 squared take 12 squared, which is 125, right?
Yeah.
Sorry, 25.
A single 25, if you say it that way.
Yes, that is a Pythagorean triple. 5, 12, 13. So we have our radius here. I should have called that R. I don't know why I used X. R.
Ooh-ar.
So let's change that actually. R, R, R. R, R, R. Okay. What's a pirate's favorite shape?
Oh, don't. I love to stop and think about it. Pirates.
Yeah. I just thought it'd be a circle because it has an R.
As an R radius.
That's a terrible joke.
You know what I'm gonna ask? I'm gonna ask ChatGPT what a joke for about pirates' favorite shape.
Okay, good idea. See what it comes up with. Can it tell jokes?
Man, have you not asked it to tell you jokes yet?
No.
Oh, you have to. It's funny that you can say, write me like 10 jokes. This is so funny.
Okay, so in this compound shape we have, I imagine this is a cone. It doesn't actually say that's a cone, but I imagine there's a cone on top of this hemisphere.
That is a cone, yes.
So we need to know how to find the volume of a sphere, and we need to know how to find the volume of a cone. These are things that you don't have to memorize for GCSEs. They'll give you those in a question, but it's also useful to know them anyway, so it's not a waste of time memorizing these. So a sphere is 4/3 pi r cubed, and which is also equal to the surface area of something, but I can't exactly remember. And the volume of a cone is 1/3 of a cylinder with the same height, so it's pi, 1/3 pi r squared h. Okay, so we have our formulas, and so the volume of this hemisphere is going to be half the volume of the sphere with the same radius. We know the radius is r now, is 5. So the volume of this hemisphere is going to be 4/3 pi times 5 cubed times a half. So this is going to be 2/3 times 125 pi, and there's not really, well, I guess we can multiply 125 by 2, so that's 250 on 3 pi. That's the volume of the hemisphere. Then the volume of the cone is going to be 1/3 pi r is again 5, and then the height is 12. Okay, so 12 divided by 3 gives us a nice whole number of 4. Multiply that by 25, and then 4 times 25 is 100 pi. Then we just add these together, which is still going to give us a, I guess we could divide 250 divided by 3. No, it doesn't go nicely. Well, let's just write that as a mixed number. That would be 80 and oops, no, not 80. 240, 83 and a third. 83 and a third, I believe. So then the total volume is going to be 183 and a third pi, if I did that conversion correctly. And I didn't make any other arithmetic errors.
I trust you so much. I'm sorry, I've been I've been asking questions to the AI.
Any good jokes?
It's so terrible. It's terrible. All right, so the first one I said, write a joke about what is a pirate's favorite shape. Like, straightforward. It said, why is a pirate's favorite shape a rectangle?
Okay.
Because it's adorable.
What?
It doesn't even make sense. It's like, I get it, like it's adorable, but it's nothing to do with pirate, right? It just said a joke about someone who happened to be a pirate. And then I said, okay, give me another one where the punchline is something to do with pirates. And he said, why did the pirate refuse to take his medicine? He said, "Arr, I be afraid it's just a placebo." It's just not even funny. So it seemed to forget that I asked it for a shape. So I went back to shapes. Like the whole conversation is awful. They did come up with your circle one though. It said, "Tell me a pirate joke about shapes and pirate common phrases." And it said, "Why was a pirate's favorite shape a circle?" And it's because it was always around the bend. It just doesn't make sense. It's not funny. I mean, it does tell jokes. Clearly, it's like jokes that it has in its memory. But anything new is just a load of rubbish. It's not. It doesn't quite get the nuance.
Have you ever watched those movies written by AI or comedy specials written by AI?
No, actually.
YouTube. It's like a whole comedy, like a half an hour comedy sketch, written by an AI, and it's just like full of that absolute nonsense.
Oh, I've seen some people like asking it to do stuff like that. You could, I mean, when you're waiting to actually log in, it's sometimes like, write me a pirate's phrase about why we can't log in, or write me a sonnet about why we can't log in. And it could do some pretty funny dialogues, but I think it's going to change a lot of things for people. It's a pretty good assistant for some things and really bad at others. Okay, that's a good question out of the way. We've got the volume of the sphere, and I like the fact that you were using fractions there. That's like, it's a bold and great move. And for some reason, I went into decimals myself. Can't tell you why. I think it's a good idea that I go to a different page for the next question, just in case we want to go back to it. And it's probably true that if we haven't gone back to it fairly soon, we won't go back to it at all. So I'm going with that one. Okay, what about this one? I liked this one because it feels fairly simple. It's no picture, but it's still it's somewhat interesting. I think you have to know a little bit about, I guess, the different sciences in some way, almost like physics. So a spherical drop of oil with a diameter of 3 millimeters falls onto a water surface and produces a circular oil film of radius 10 centimeters. Calculate the thickness of the oil film. Is that interesting, right?
Yeah, it's similar to the question with the barrel.
It is similar. But what do you know about? I mean, obviously it's a water surface and it's circular. But what we know about oil and water is they don't mix. So you're going to have, you know, whatever this is onto a water surface, and then you're going to have on the top of that some sort of oil spillage, shall we say. And it's just going to be a cylinder, right? And we're going to talk about what we know about that cylinder. Yeah, that's not too bad. I was worried about how that would go. And we've got a diameter of 3. So first of all, this is a drop. It's not going to be perfect, but it's spherical. And this drop has a radius of 3 millimeters. Oh, diameter. Pardon me. So the radius would be 3/2 millimeters. Look at me and my double checking. Always double checking. This is an interesting thought actually. If we convert this to, in fact, could I do that and keep? So 3 millimeters would be 0. Yeah, I think I'll probably have to do it into centimeters. So 0.3. So we're going to say 3/10 of a centimeter. Only because when it comes to it, in fact, no, that's the, oh, for goodness sake, how many times am I going to do this? Right, so I'm going to write it out here. 3 millimeters equals 0.3 centimeters. And no, it doesn't. Or 0.3 millimeters, which equals, in terms of, I don't know what I'm doing here. Can I just reset myself? I went on ChatGPT, and it's all over. 3 millimeters is equal to 0.3 centimeters, as I did originally write. Okay.
You're definitely a stats major. You prefer your decimals.
It's not always true, but tonight I seem to be clinging to them. I don't know what it is. So this is in centimeters now, which is really useful, but this is diameter. So we actually need half of that. So we replace that in here. That would be 3/10 normally, but then half of that would be 3/20. Radius. Whew. Okay, we got there. So this little bit here, and from this, I suppose we could find the volume. Try to keep it as fractions, I suppose, this time. 4/3 pi and 3/20 cubed. Let's get a refresh on what we're doing. The thickness of this oil film. So what we do know is the radius of this is equal to 10 cent. That's rather wide, isn't it? And we're looking for this, which I suppose we could call it the thickness of the oil film. We could call it height. So an expression for the, we don't know the volume of that. We know that the volume is equal to this. Does that tidy up at all? 27 times 4. We got 108, if I can find my pen, out in the ether. And then we've got 20 cubed, which is 8,000 times 3. So we've got 24. I mean, is this the right place for a fraction? It's getting a bit crazy. I'm wondering if I did the division there. I think I could probably get 9 in there. That'd be 12, wouldn't it? So divide by 12 would work. And that would go down to 2,000. That's about as nice as it gets in terms of fractions and stuff. Be interested what that is as a decimal. Probably really small, so maybe fractions are a nice thing to work with here. Okie doke. This is the volume, and it's going to be equal to this cylinder of oil. And we've got another expression to find. So, volume of the cylinder is equal to pi r squared h again, so we will just do it as it is. Yep. And then pi times 100 times h, which is the unknown. We know that this is equal to this on the left. So 100 pi, if you'll allow me to rearrange, with an h, is equal to 9 over 2,000 pi. Anything clever here? I think so. This is a good example of what we were talking about earlier. I wish I had more space, but I just have to put up with it. I'm going to scroll down. It's a good example of where if we keep it like the fraction, right, we get some cancellations. So we can move that over there to be 2,000 with another couple of, what do you call it? Another couple of zeros, and we've got the pi in there as well, beg your pardon. And then we can cancel a little bit, right? In fact, do we really want to move that over? Probably not, because the 9 is not going to cancel there. I guess we could probably keep it in our minds that it's good enough that we can cancel these pi, and then we can divide by 100. And if we divide by 100, it's the same as multiplying by 1 over 100. So then h is going to be equal to 9 over 2,000 with a couple of extra zeros. And the pi's will disappear. But this doesn't say anything about giving it as in terms of pi. So just out of interest, on the calculator is really rather small. Question is this small, 4.5 times 10 to the minus 5. I'm shocked how many people don't read the calculator this way, but this is standard form, isn't it? And there are some calculators that write it like 4.5 times e to the minus 5, if I remember. There's all sorts of strange expressions out there. But it just means that if we have the negative, that's how many times you're going to make this smaller, how many, like order of 10. So this is going to divide, and if you want to think about it in interesting terms, which way the decimal place is going, it's going to be going this way to make it smaller. So it's 1 to get it out there, so a further 1, 2, 3, 4 moves. And that's how small it is we're talking. And the final answer, we convert it to centimeters. Very small. Negligible. At this sort of level, it's interesting that you wouldn't even barely see that, but there could be a layer, like a very thin layer of oil on the top of a surface of water. I've seen that before, where maybe you've got like a face cream or something, and you just like, I don't know, you splash your face with it, and then it's in the water, but it's a very thin layer on top.
Yeah, I think it makes sense in the context of the question.
Because it's a very small amount of oil.
Layer of oil on a water surface wouldn't be very thick.
Not at all. Okay, let's get the next question in. We're going to go to
Wait,
page...
the last one, or my last one?
Yeah, sure. We'll go for one that looks fairly challenging. What do we think was the hardest one? I don't know if it's hard, but I'd like to do it. And I mean, I'm going to help you with it, but it's your turn. So you happy to do it?
Sure. It's a cool diagram.
Pretty well done, huh?
It's like a diamond or something. A conservatory has the shape of a pyramid on top of a prism. Okay, so hexagonal base pyramid. The base of the prism and the base of the pyramid are regular hexagons of side length 1.2 meters. The height of the prism is 2.1 meters and the height of the pyramid is 0.6 meters. Calculate the volume of the conservatory correct to 3 significant figures. Okay. Well, a hexagonal prism is fine. I guess the pyramid is a third of that, right? That's the general rule.
That is a general rule, no matter what the shape is on that base.
Yeah. All right. Forgetting how to find the area of the hexagon. There's a nice formula for it.
Is there actually? I typically
Sure.
I typically break it into equilateral triangles, but I didn't know if there was a formula.
Yeah. I'm going to cheat and look it up. Yeah, it's this. So area of a hexagon. I probably should have done it that way, but you basically derive this every time you work out the area of a hexagon.
Oh, do
3
tell.
root 3 on 2a squared. Where a is the side length of the hexagon. And the 3 on 2 root 3 comes from where does that come from? Three on 2 root 3.
I'm going to slowly draw a hexagon here.
Oh no, it's like yeah, if you think about oh well, there's a number of ways to think about it. You think about it as 2 trapeziums or whatever, but I think it's actually 3 times root 3 on 2 is like 3 of those triangles at any rate. It's not difficult to derive the formula. Okay, so we can find the area of the hexagon if we have a, so that's going to be 3 root 3 on 2 times 1.2 squared. Guess we're going to need a calculator. 1.2 squared, 144, 1.44. Yeah, it's just a calculated question, I guess. Then the volume of prism is going to be this 3 root 3 on 2 times 1.2 squared multiplied by the height, which is 2.1, and then the volume of the pyramid Well, as we said, a pyramid is a third of the prism that lies within. So the prism, the hexagonal prism there would be 3 root 3 on 2 times 1.2 squared times the height, which is 0.6. And then if we take a third of that, we should get the volume of the pyramid. And then we just stick that in a calculator, I guess. So, yeah, 3 root 3 times 1.2 squared times 2.1 divided by 2. This is 7.86 approximately. And then the volume of the pyramid is 3 root 3 times 1.2 squared times 0.6 divided by 6, because I divided by 2 and by 3. Which is a lot less. Guess that's fine. 0.75 approximately. And so the total volume comes out to be these things added together. So 7.86 plus 0.75. Approximately 8.61. Hopefully that's correct. Meters cubed.
Just working this through, like, it's pretty bad.
Okay, so 10, 3/5, so 10 of 60 is root 3.
Because it will always be 10 of 60. Hmm.
$22. Seems like I made a mistake.
Oh, I've not got to the fully end. This is just the area of the base of the...
Yeah, but I've my final volume of the prism was only 7 point something.
Well, you do times it by a third. I mean, it could get smaller at the top there. A third of the base times height, 0.6. Overall, I got 51.
Oh.
Yeah, I don't know.
Who's right?
It's a good question. I'm just gonna get the answer now. Woohoo! Opens at the lovely place. I think we've got the same one here. So, Interesting. You'll be interested to see if I get the right one for the numbers on the side here. So 0.6. Did I use the wrong numbers? I used 3/5, which is 0.6, right?
What was the final solution?
1.03. Yeah, I'm just trying to find it. Ah, here we go. It's 8.61 like you got. So where did my one go wrong? I've used so many fractions, it's hard to tell the decimal equivalent.
3/5, so 5, so 1.2, 6/5, half of those 3/5. Area, so the height, n of
That O is opposite, right?
Jason. Oh, right. 3 of 5. Okay.
Area is a half, and then 6. That's the opposite, and then 6. Oh, is that what it is? No, that's right. 6/5 is 1.2 times by the height, which is 3√3/5, and then halved again. That's the area of one triangle. So that's the area of one triangle there. And then the total area, which is 6 times that, would be this. Unless that's been put in the calculator wrong.
Where's the 54 come from?
Well, I put it in the calculator at that point, and that's what's come out. So I wonder, unless that's what's wrong. 3√3
54
divided by 5, and then we'll divide that by 2. Oh, sorry, times it by half, actually, that's a bit easier. And then times that by 6/5. Well, yeah, that is where it's gone wrong. For some reason, I must have, in the calculator, put that in a bit funny. So yeah, that's more like it. And if I times that by 6, then I get 54. So I'd already times it by 6. So if I divide my answer by 6, would I get 8.61?
Yeah.
I think so, because I've times it by 6 one too many times.
Well, that's just the hexagon.
What I did with this number here, which is the base, that was the answer. So it would be the base times the height. So it's going to be answer times 2.1 plus the top part, which is the answer again, which is the area of the bottom, multiplied by the 0.6, and then divided by 3. So multiplied by 1/3. Yeah, there I go. I get something slightly off though. It's really strange. I get 8.604828.
Well, I used these rounded numbers.
Oh, that might be what it is then.
What if they did that?
Well, the question that we got this from, they have used rounded values as well. That's why they got 8.61.
Okay.
But the more true version would be here. But obviously, isn't it nice if you could use that formula, if you could remember it?
Yeah, so let's derive that quickly, because you've done most of the work here. So let's call this A. This would be A on 2. So then the area of that triangle is the area of this triangle
A over
is
2
always going
1060.
to be
But 1060 is an exact value.
A. It's always going to be A times the height, which would be A onto root 3.
Yeah.
And then we have 6 of those. Wait. So the base times the height, divided by 2. And then we have 6 of those triangles. 1, 2, 3, 4, 5, 6 times 6. So this comes out to be A squared on 4 root 3 times 6, which is 3 root 3 on 2 A squared, right?
That's the one, isn't it? Yeah, there you go.
That's one way you can derive it.
If you want to remember it, because you've got a really good memory, why not?
Yeah,
Skipping steps.
How
All right.
useful would that be? I'm not sure. I didn't remember it. I double checked it. I just Googled it for this question.
It's such a rare thing. So would you derive it in the exam? Probably not. You'd probably just go through it.
Yeah.
But hey, there you go. All right. So let's finish up. Let's end the stream here, and hopefully that was useful to some people asking for 3D shapes and volumes and surface area practice questions. If you're watching this on the replay, then that's still going to be useful, even if you couldn't make it tonight. So thanks for coming, whoever did, and catch you next time.
Thanks, guys. See ya.